Welcome back to the Deep Dive. Today, we're actually taking a bit of a trip back to 1970.
Oh, interesting. What's the focus?
We're diving into the foundational ancestor of modern software development, the Waterfall Model.
Ah, waterfall. Right. This isn't just, a history lesson. It's really the framework that first defined structure for the whole industry.
Exactly. And it matters because, well, it was the first widely adopted process model out there.
It really set the stage, didn't it, for how we think about control, about documentation, all of that in software projects.
And when we talk about this model, we're really talking about a linear sequential life cycle. The name itself kind of gives it away.
It does. It flows in just one direction, steadily downwards, like a waterfall.
Okay, go back up.
Nope. Very simple concept, and that simplicity was actually intentional.
So the mission for you listening today is to really get why this very rigid sequential process was invented by Winston W. Royce back then.
And crucially, what were the fundamental limitations that basically forced the industry to look for alternatives for most modern projects anyway?
Okay, so let's unpack that structure, that flow. The absolute defining rule is that sequential handoff, isn't it?
It is. Phases just cannot overlap, period. You have to be completely finished, signed off on step A before you can even think about starting step B.
It sounds less like development and more like, I don't know, a manufacturing assembly line.
That's a great analogy, actually. The outcome of one phase acts as the formal signed-off input for the very next one.
Only forward.
Only forward. And this strict mechanism, it was designed to ensure, total accountability at every single checkpoint.
Right, and that starts right at the very beginning, phase one, requirement gathering and analysis.
This is an absolute critical moment. You've got the development team, the customer, stakeholders all sitting down to capture every single system requirement. Functionality, performance, security, absolutely everything.
And the analysis part, that's about making sure it's perfect.
Pretty much. The goal of analysis is to iron out any incompleteness, any inconsistency. It has to be crystal clear.
And the output of that phase is, well, it's hugely important, isn't it? The software requirement specification document, the SRS.
Absolutely crucial. That document isn't just like meeting notes. It serves as the formal binding contract between the dev team and the customer.
A contract. Okay, so once the customer signs off on that.
The requirements are locked, fixed, no changes allowed.
Wow. Okay.
And if you have that flawless contract, then you move straight into phase two, system design.
This is where you translate what the requirements into the how, the actual architecture.
Exactly. Taking those requirements from the SRS and figuring out how to build it.
So how do they tackle designing a whole system just based on a document? Do they just start sketching out ideas?
Well, they break it down systematically, usually into two main parts.
Okay.
You can think of the high-level design, or HLD, as, say, the main architectural blueprint for a house.
Right. The overall structure, foundation, maybe major systems.
Precisely. Floor plan, key algorithms, how data flows. Then you have the low-level design, the LLD.
And that's the nitty-gritty.
That's the detailed spec for every little component, every user interface element, every database field, almost like specifying the doorknobs and light switches.
Got it. These two together, the HLD and LLD, they produce another formal document.
Yes, the software design document, or SDD. That's the output for this phase.
Okay, so that highly detailed design then dictates phase three, implementation, or development. Coding.
Correct. The designers hand over the SDD to the programmers, the coders.
And their job is just to translate that plan directly into source code.
Exactly. Using whatever programming languages were decided on. And development is usually done module by module.
In smaller chunks, like units.
Yeah, units. Yeah. Manageable pieces. And as soon as a single unit is coded, it gets its own testing, unit testing.
Just to make sure that one piece works correctly on its own.
Right, in isolation. Does the specific function do what the LLD said it should do?
Okay. And once all those separate, isolated pieces are coded and unit tested, we hit phase four, integration and testing.
Ah, yes. And this is where the technical risk really starts to peak.
Why is that? Because you're finally putting it all together.
Exactly. And the sheer risk here is tied to how it's put together. Integration is typically done as a single, huge event at the very end.
Like a big bang.
Precisely. The Big Bang integration. All those units that were built and tested separately are suddenly smashed together to form the complete system.
And if they don't fit or don't talk to each other right.
Then you only find out about that fundamental flaw right at the end. Maybe the interfaces were misunderstood or designed incorrectly based on the SDD. And the team only discovers this when they try to bolt it all together very late in the game.
So you're essentially building blindfolded until that final step and then just hoping it all works.
It can feel a bit like that, yes. It carries significant risk.
Okay, so let's say the Big Bang integration does work somehow. What testing happens next?
Well, then you move into broader system testing. This usually involves a few stages.
All right.
First, alpha testing, which is done internally by the development team, maybe the QA team.
Okay.
Then beta testing. That's where you give it to a select group of friendly customers or end users to try it in a more real-world setting. Find bugs the internal team missed.
Right, get some external eyes on it.
Exactly. And then comes the final gate, acceptance testing.
And that's the original customer again?
Yes. They test the software against that original SRS contract. Does it do everything we agreed on back in phase 1? They then make the official call, accept or reject.
Okay. Assuming the client accepts it, we finally flow into phase 5, deployment of system or operation.
Right. The product, having passed all tests, is deployed into the customer's actual working environment. Or, released onto the market if it's a commercial product.
Is this phase usually complex?
It can be, depending on the system. Often involves setting up servers, databases, maybe migrating data, and definitely providing user training on the finished product. But it's usually more logistical than developmental.
Got it. And that brings us to the final phase, phase 6, maintenance. This isn't just about fixing minor bugs after launch, is it?
Oh, far from it. Maintenance is often the longest phase of the entire life cycle, and statistically, it can be the most expensive.
Really? How expensive are we talking?
Well, some studies suggest the effort spent on maintenance can be up to maybe even over 60% of the total effort spent to develop the software in the first place.
60%? That's huge. What drives that massive cost? Why so much effort after it's supposedly finished?
It usually breaks down into 3 main types of maintenance activity.
Okay.
First, corrective maintenance. This is fixing the bugs, the errors that actually slip through all the testing phases, latent defects.
The ones you didn't catch earlier.
Exactly. Second, perfective maintenance. This is about enhancing the software, adding new features, or improving performance based on customer requests after deployment.
So evolving the product.
Right. And third, adaptive maintenance. This involves modifying the software so it can run in a new or changed environment. Maybe a new operating system version comes out, or new hardware, or new regulations.
And that high cost, especially the corrective part, feels like a direct consequence of that rigid upfront process, doesn't it? No room to fix things early means you pay for it later.
That's a very common criticism, yes. The lack of early feedback and iteration means problems discovered post-launch can be very expensive to fix.
So, okay, given that intense rigidity, the Big Bang integration risk, and this potentially huge maintenance bill, why would any team actually choose this model today? What's the upside?
Predictability and control, that's the main draw.
How so?
Well, the waterfall model is highly structured, very systematic. It shines when certainty and meticulous documentation are paramount. It gives management, stakeholders, even regulators, excellent visibility and control points.
So if you need absolute structure, waterfall's the way to go.
It can be, yes, when the environment demands it.
Our research pointed to some pretty specific conditions where it might still be applied. We're not talking about like building the next social media app, are we?
Definitely not, no. You'd consider waterfall when, first and foremost, the requirements are incredibly well understood, fully documented, clear, fixed, and stable.
Meaning there's almost zero chance they'll change during the project.
Exactly. Low risk of change is key. Also, the technology being used should be well understood and not dynamic or rapidly evolving.
And the project itself.
Ideally, it should be relatively short or simple, not overly complex, or a long, ongoing initiative where requirements are likely to drift.
Okay, that makes sense. And there was another key area, regulation and safety.
Ah, yes. Crucial point. For safety-critical systems, think aerospace, medical devices, maybe some government or defense projects. Waterfall is sometimes still used.
Why there specifically?
Because regulatory compliance is absolutely critical. These projects often require exhaustive documentation at every single step, proving the process was followed meticulously. Auditors need to verify each phase.
So the model's emphasis on documentation becomes a major strength in that context.
Precisely. It naturally enforces good habits like define before design and design before code. It allows for clear departmentalization and control because every phase has very specific, defined deliverables and review milestones.
Okay, so that structure is the big advantage. But you mentioned earlier that rigidity is also its biggest flaw.
It is. They're two sides of the same coin. While it offers control, that rigidity is the major disadvantage for most modern software needs. The core drawback is that inherent lack of an easy feedback path or a way to revise earlier decisions.
Right, it just assumes perfection in those early phases, especially requirements.
It really does. And the consequences of finding an error late in the game, say a flaw traced back to the original design discovered during testing,
Catastrophic.
they can be project ending, honestly. If requirements genuinely need to change midstream or if a fundamental design flaw surfaces late, adjusting the scope means essentially tearing up that initial SRS contract, potentially going back to the beginning. The cost and time implications are enormous. The amount of risk tied to any change is immense.
So let's explicitly list those critical drawbacks, things that really push the industry towards newer models.
Okay. First big one, late software production. Because you must follow the sequence, no working version of the software is actually produced or demonstrable until very late in the life cycle.
Usually not until that integration and testing phase.
Right, which means defects are also detected very late, and late defects are always more expensive and time-consuming to fix than ones caught early.
And if the client doesn't see anything tangible, anything working until phase 4,
Their valuable feedback is essentially locked out until it's potentially too late or too costly to implement easily, which leads to the second drawback, limited feedback.
stakeholder involvement is pretty much front-loaded, right?
Yeah.
Heavy in phase 1, then they basically wait.
Typically, yes. Requirements gathering, sign off, and then maybe they reappear for acceptance testing at the end. Modern development absolutely thrives on continuous iterative feedback. Waterfall just doesn't facilitate that.
Okay, late software, limited feedback. And we keep circling back to that high-risk moment.
The integration bottlenecks, yes. That big bang integration right at the end is a massive concentration of risk.
Because you haven't tested how the pieces fit together until then.
Exactly. It prevents the team from identifying potential technological roadblocks or even business logic bottlenecks early on when they'd be relatively cheap and easy to address.
If a core design choice made way back in phase 2 turns out to be technically flawed or doesn't meet a real need discovered in phase 4.
The financial fallout, the delays, it can be immense. It's a huge gamble piled up towards the end.
Right. Okay, to make this really concrete for everyone listening, let's walk through an example. Something complex that might have traditionally used Waterfall. How about developing a major online banking system?
Oh, that's a perfect example. Especially for the initial core platform build, you can see the waterfall mindset fitting quite well, historically at least.
So phase 1, analysis.
Absolutely critical. Gathering every single detail transaction types, fund transfers, security protocols, regulatory compliance needs, audit trails. That SRS has to be watertight. You can't afford ambiguity when dealing with people's money and strict regulations.
Makes sense. Security can't be an afterthought.
Not at all. Which flows into phase 2, design. This would be hyper-focused on robust security architecture, encryption methods, secure database design for sensitive data, multi-factor authentication logic.
Things you really need to get right from the start.
Exactly.
Yeah.
There's very little room for let's try this security approach and see. The core design needs to be provably secure, often to satisfy regulators before coding even starts. The SDD would be exhaustive.
Then phase 3, implementation. Coders build exactly to that secure design.
Precisely. Likely with lots of internal checks. Made dummy runs using provisional data to meticulously check transaction accuracy, often matching results against criteria set by banking experts or auditors.
And phase 4, testing. The focus here would be
Overwhelmingly on security vulnerability testing, penetration testing, checking data integrity, accuracy under load, performance, ensuring the user interface is clear and prevents errors, making sure it meets all those SRS requirements.
in this kind of high-stakes scenario, that linear flow, that heavy documentation at each stage, it actually provides confidence, doesn't it?
It does, especially for external parties like regulators and auditors. They can review the detailed documentation created at each phase gate before giving the green light for the system to go live. It provides an audit trail.
But then we hit phase 6, maintenance again, even for a bank system.
And that's where even a waterfall-built system starts to look more iterative in practice, right? Maintenance is constant.
Like security patches.
Definitely. Implementing urgent security patches, fixing newly discovered or newly relevant vulnerabilities, but also perfective and adaptive changes.
Adding new features.
Sure, maybe adding new features demanded by the market, like mobile check deposit, or integrating with new payment systems, or maybe features like instant loan applications, plus adapting to changing banking regulations.
So it might start as a rigid, structured build for the core.
But its actual lifespan becomes defined by ongoing, often expensive adaptation and enhancement. That maintenance phase really highlights the long-term costs.
Okay, this really brings us towards the end of our dive today. Let's recap the main takeaways.
Sure.
The waterfall model. It's the highly structured, document-heavy pioneer of software development methodologies.
Right. It prioritizes absolute clarity, upfront planning, and stability over flexibility and speed. It was really born from an era where tackling large, complex projects seemed to require these fixed, auditable requirements.
Control was key.
Control and predictability, yes.
Yeah.
But the lasting implication, the big takeaway for today, because it demands those fixed requirements upfront and heavily discourages or makes it very costly to go backward, it's fundamentally ill-suited for the fast-paced modern world.
Where user needs change constantly.
Exactly. Constantly changing user needs, rapid technological shifts, intense competitive markets. Waterfall just isn't built for that kind of dynamic environment.
So pretty much every other SDLC model we might discuss later.
Iterative, agile, spiral, V model. They are, in essence, derivatives or reactions. They were specifically designed to overcome Waterfall's core inflexibility, especially that high risk associated with discovering defects so late in the process.
Okay, so here's our final thought for you, the listener, to maybe chew on.
Go for it.
If this model's biggest, most fundamental weakness is that no working software is produced until late, which leads directly to those expensive, late-stage defects.
Oh.
What would a developer or a project manager logically do next to fix that specific problem?
Good question.
How would you get functional, potentially shippable software into the client's hands, not just once at the very end, but repeatedly, quickly throughout the project?
Something to ponder. How do you introduce iteration?
Think about that until next time. We'll see you on the next deep dive.